So I'm going to be landing on a lot of the same places that Phil actually landed because I, too, have a real heart for algorithms. It'll just be a lot less computer science because, unlike probably most people in this room, I really like Fortran. So some of the code examples are in Fortran, so try to hold your breakfast when those come up. So I'm going to talk about use of GPUs in supercomputing, and I want this to be a real ground level, hands-on kind of talk. Basic, but giving you a real feel for what you should think of in your code, in your field. So sure enough, the first thing I want to talk about is the motivation of why we're doing this and the fact that data movement really is the #1 cost that you're going to have to deal with. So why use GPUs in the first place? Power consumption is becoming the dominant cost of maintaining a supercomputing center. And so we want to keep the power costs down as much as possible. We want more performance, but we don't want to pay for it with megawatts. So GPUs are one approach to using this. There are other approaches, but we're going to focus on GPUs here. So an example from Jaguar XT5 that we had a couple years back had 1.8 petaflops on the top 500 list, and we used about 7 megawatts of power. According to 2011 data at the time, that's 5,400 houses worth of electricity. You can imagine how much electricity that really is. So you don't want to be going into gigawatts. We're going to have a couple of dedicated power plants just for the supercomputer. And I'm not sure DOE can afford that. So the Titan XK7 is an example of what happens when we throw an accelerator on there. In this case, it was an NVIDIA GPU, Kepler series. 18 petaflops were obtained with the LINPACK benchmark at 8 megawatts of power. So we got an order of magnitude more performance according to this benchmark with a very marginal increase in power. So this is almost an order of magnitude. So this is just an example of what happens with the use of GPUs. Now, the LINPACK benchmark is not really a good proxy for scientific applications. It's really not. It was actually meant to bring out the performance on the system. But we still get a large increase in performance with modest increase in power. So there's still quite a benefit. So massively parallel computers, they're architectured in a hierarchy like you just heard. There's a collection of cabinets. You can see how old the slide is because I have Jaguar up there instead of Titan. So this is a borrowed slide from a previous presentation. Each cabinet is going to have a series of blades, order of tens of blades. Each blade has interconnect to communicate to other blades. And it has a number of nodes on it. Every node has its own memory, and it has its own processing. Nodes share data over fast specialized networks. Usually it's some kind of special technology by the company that's making your supercomputer. And so the primary difficulty of computing, before we get there, I want to talk about what peak performance means, or rather what it does not mean. This is a fictitious perfect world number where if data were to magically teleport into your registers, this is the kind of performance you would get. So you got the cycles per second of your core, your hertz, multiplied by how many floating point instructions per cycle. You could throw hyperthreading in here, where they share the same instruction scheduler. You have the number of cores you have per processor, the number of processors per node, and the number of nodes. So it's very straightforward. This is how much churning you can do if the data was just magically to appear. This has little bearing on science. It has little bearing on anything because data doesn't magically appear. It has to travel over wires. So if you take nothing and you multiply by nothing, you get nothing. It's not a very exciting result. That's why peak performance ultimately is not the most exciting number. Processors need useful data in order to give you something useful, and data movement is far slower than processing. We'll get more into this. Before we get there, there's two concepts I want to go over with data transfer. First, data transfers over wires before it gets into the registers for use by either the GPU or the CPU. There's two main properties to each of these wires. One is latency and the other is bandwidth. Latency is an amount of time. It's the amount of time it takes to search around in the reservoir of memory, find the data that starts your offset, and to get that data out and through the wire into where it needs to go. So this is a time delay that gets from one end to the other. Bandwidth is the amount of data you can pump through, assuming that you're asking for a lot of data from that offset. You can churn through this much data in the pipe per second. So this is a rate. And so the slowest part of the entire supercomputer is certainly going to be disk I/O. Well, tape would be worse, but you don't do that during a job submission. You do that outside during analysis. So this is the slowest component. The amount of disk I/O that you do is application dependent. I actually know applications that can use the entire supercomputer and output barely megabytes of data. That's not common, so most of them put out terabytes, petabytes of data. You need data to initialize your model. You need to write history files out to analyze later, or while else are you using a supercomputer. You need restart files in case part of your nodes go down. The technology for restarting is not the greatest at this point. There's a lot of research going on, but it hasn't made its way all the way to the front yet. But you need to restart the simulation. So this is needed for analysis and post-proc. The second slowest part of communicating data across the network, this actually happens in your job more. This is communicating over the network, mainly Npi. There's some global arrays, but as far as the projects that compose our machine, most of them are Npi. So this is where you'd see a two-dimensional torus up here. I think I have a laser, yeah. So you have connections in both dimensions. Titan's actually a three-dimensional torus, and you have square root of the number of nodes over 2, amount of time to get from one point of the system to another. So there's different modes of communication. You can do all-to-alls, where every point communicates with every node. Point-to-point, where one node communicates only to its neighbor or another node. And you have reductions, where it all comes down to a single node, then broadcast back out. So there's a lot of ways to do this. But that's the second part. And before we get to GPUs, we have to realize that we still have to respect Npi locality. And finally, before we go over to GPUs, the next level that you have to pay attention to is going to be DRAM. DRAM is many hundreds of clock cycles to find memory. That's the latency. So it's pretty low latency. It's got a bandwidth that's a lot higher than Npi, but it's also still at least 100 times too slow for the processor. The processor can churn data 100 times faster than you can actually pump it through. So even in a perfect world, if you're entirely bandwidth limited from DRAM, you still are 100 times too slow, slower than peak. So considering that you want quarter peak, half peak kind of numbers, you're not getting anywhere close unless you're caching through multiple levels like you heard earlier. So you put some data into cache and you reuse it a whole bunch. The cache is much higher latency. You pull it from the cache into register space, and then you can finally do your computations. So it's gone from disk all the way through nodes, through DRAM, through cache to the register. So that's your memory hierarchy for a typical supercomputer. This doesn't change, so if anything, we're actually adding constraints to it. So basic GPU architecture, the first thing I want to show you is this PCI Express bus. This is the first thing you'll notice when you're moving to using any accelerator, including Intel's current mic architecture. You have a PCI Express bus that is, this is the traffic block here. This is very slow. It's also extremely high latency. So the GPU has its own reservoir of memory. It's about 3 to 4 times faster than main memory. So even if you're memory limited, you're still going to see a 3 to 4 times increase in your throughput compared to the CPU. But you actually have to get the data there across the PCI Express bus. It connects the two. It connects your main system memory to your GPU memory. It has a latency that's about 1,000 times higher than Npi, at least for Titan. Npi has a latency of about a microsecond going from one node to the next. The PCI Express bus is more like a millisecond. So it's pretty painful if you're not pumping through much data. And it's 864 times slower than peak flops on Titan. And that's double precision flops. The single precision flops are 3 times that. So this is the kind of numbers we're looking for. You cannot mindlessly pump data through the PCI Express bus without either hiding it, overlapping it, or minimizing it. So this is an example of what a GPU is. All it is a collection of multiprocessors. So it's just another hierarchy of computing. Instead of one multiprocessor, now you have, order 16 multiprocessors, maybe 32 on the latest architectures. This is a little bit of an old GPU, but it's going to have its fast memory connected to memory controllers that pump data through an L2 cache to smooth everything out in the accesses. It's going to make its way to every one of these multiprocessors. They share the same cache at that level. So In this case, it has 15 of these so-called SMX processors. It's just a niche term from NVIDIA for streaming multiprocessor next generation. But if you want to take a look inside of one of these, well, before we get there, these were made for gaming. So you're mapping textures to geometric objects. You're basically applying the same operation multiple times, a bunch of times. So you'll take, this part of the texture file, you map it to this part of the geometric object, and you just do it over and over and over again. So you want to perform the same operation on as many different data as you can. Luckily, a lot of scientific applications already do this, especially stencil applications, combustion, climate, transport, things like that. So looking inside of one of these multiprocessors, this is the view we have. Here, there's a lot of things to look at. I just want to pay attention to these green cores for single precision and these yellow cores for double precision. On Kepler, at least, you get a big benefit if you can go in single precision instead of double. You can run 3 times as many operations per second in single precision because there's 3 times as many cores. And also, your throughput in memory is twice as fast because a piece of data is half the size. So these are really dumb cores. They don't do anything for you, really. You tell them what you want them to do, and they do it. They don't do anything fancy. They don't move operations out of order to get the instruction stream to handle more efficiently. They don't cache for you, at least not on the latest Kepler architecture. They got rid of hardware cache. You have to manage it yourself. None of the branch prediction, none of the things that you're used to on a CPU core are here anymore. You have to either have the compiler do it for you, or you have to do it yourself. So just as you heard earlier, the amount of memory that you have per core is decreasing. So we only have 64 kilobytes of general cache per processor. That's less than a megabyte per GPU. That's not a lot of cache considering how much data we're supposed to be processing through this thing. So you have to be very careful about reusing data, using it as efficiently as possible once you grab it from main memory. There's also a pretty healthy register file, but it's used by the entire multiprocessor. So there's about 32 values if you're in double precision that you can store and register across the whole device. But remember, you have at least 64 cores. If you're in single precision, you have a lot more. So that just says, again, you have to be careful with what you put in register, how you use the cache, and what your algorithm's doing locally. The threads, you launch a single thread that specifies what one core will do to an arbitrary piece of data, and you launch it over all the cores, and they all do the same thing. At least they better. And you can have more than one thread per core. In fact, you should have more than one thread per core. Per GPU, you want to have tens of thousands of threads launched per device. So the threads, they can synchronize with the barrier function. They can share registers, and they can share cache, but only within a multiprocessor. You can't share this kind of stuff between multiprocessors. There's no function to do that. Otherwise, it's not a scalable way to go with many cores. So this is how the GPU industry has handled it. So some basic programming to get our feet on the ground level more, what we actually do with this device. The first thing you should always do before looking at any architecture when you're porting is profile your code. In fact, you should profile your code anyway. You want to understand where the hotspots are, where you're spending most of your time. If you're going to port it to GPUs, but you're spending most of your time in disk I/O, or you're spending most of your time in Npi, is it really going to benefit you if you go to 2 to 3 times faster on a GPU? It may not. So that's the design choice that you need to decide beforehand. But I've seen projects port their entire codes over to use GPUs when they're spending most of their time in disk I/O or some collective Npi, and it may not be worth the time that you spend porting the code. So that's something to do beforehand. Always, always, always profile your code. Is there enough user function runtime to warrant the porting is the first question. And where are the hotspots? Where are you actually spending your time in your specific code? Can you expose massive amounts of data-independent threading, meaning you're doing the exact same operation on a bunch of different data? The operations inside loops, if you have nested loops, which you should if you're porting to GPUs, it shouldn't be dependent. So triangular loop structures are often pretty difficult. There is software, especially libraries, that handle this for you, but I don't think you want to code this by hand. This is below that imaginary line where you just don't want to be touching the code, at least by hand. You want someone else to do it for you. And preferably, you want about tens of thousands of threads per GPU device. So you want to try to expose at least that much. Branching logic, if-else statements. You don't want this diverging within a single launch of threads. The threads launch about 16 instructions at a time. Some architectures launch 32 at a time. They all do literally the exact same instruction. So if one part of your if statement is doing one thing and the other part's doing another, they're going to do both of them. So you actually double the amount of time you spend in that if statement. So you only have one instruction scheduler per multiprocessor. You want to use it efficiently. So if you can actually pack the if-else statement so that within a kernel launch or within one multiprocessor, you're doing one instruction at a time, that'll give you a factor or two increase the amount of time you're spending. So is code restructuring going to be necessary? I'll go ahead and answer that for you. Yes, you're probably going to have to restructure the code. Most of the time we build our codes, for order 16, maybe 32 threads. And now we're asking for 10,000. So I think it's safe to say you're probably going to have to restructure something. And that's true for Mike as well. You're not going to get away with just 64 threads. They preferably want an order of magnitude more than that. You're going to have to restructure it anyway. So you might as well go ahead and take a look at how you can expose more threading. Because whatever architecture it's going to be, if it's power efficient, it's going to have more cores. All right, so here's where I want you to keep your breakfast. This is Fortran. I apologize. This is what I work in. I don't work in C. At least with the codes I port. With Fortran, it's column major indexing, so the first index is the one that actually loops the fastest. So this is a loop from our code. I work in the climate field, so we're reporting a climate code. You could think of it as the stencil code, essentially. And so here we're just doing a simple division operation between two pieces of data. And this is what it'll look like when you port your code over for a simple loop. The outermost loop indexes are going to become blocks. This is CUDA speak for something that goes on a multiprocessor. So if you remember that diagram, each of these blocks is going to go to a specific multiprocessor. The whole block lands on one of the multiprocessors. The inner loop, known as threads, are going to go onto the cores within a multiprocessor. So in my case, I'm in double precision. So it's each of one of these threads inside here, this is three-dimensional threading, is going to go into one of these cores. And every one of them is going to do the same operation. You want to keep the fastest varying indexes the same in your CUDA code. If it's the fastest varying index, in this case the first index, you want it to be the fastest varying in the CUDA language. So this thread X loops the fastest, Y loops the next fastest, then Z, and then your block is what loops the next. So just keep that in mind when you're porting over. You basically give a template operation, and then you specify the data that you do it on using these thread indexes here. So same operation, multiple data. You need to think differently about the way that you do threading. The way that memory is accessed on the GPU is not the same as you're used to on the CPU. You heard about cache locality earlier, and this is how you would code it to respect locality in Fortran on a traditional CPU. Why? Because each of the cores is going down the call tree, and it's executing these things in order that you put them. It's going depth first. If you did this on the GPU, this code would perform extremely poorly, as we found out the hard way, because we didn't have someone to tell us ahead of time, and I hadn't quite figured out how they access memory. So the CPU is taking, a single thread will take this, and it'll go down the call tree of, what you're telling it to do. It's very straightforward. GPU does not do this. It takes a single instruction at a time, and it launches it over a bunch of threads. So this one instruction here is going to be launched over 32 threads, and I is what's actually changing the fastest in this case, because that's the first thread index. So you take one instruction, launch it over a bunch of cores, and that first index is actually not what's changing the fastest, and in this case, you're not accessing memory very well at all. So a simple transformation of this to the end, and suddenly, with I being your first index, you're now accessing it sequentially. Also, on a CPU, you're probably used to being able to stride data and still get decent amount of performance. Maybe you'll go every 8th. As long as you keep alignment the same, maybe every 64th byte, you'll still get decent performance out of it. That's not true on the GPU anymore. You really want to be sequential whenever possible. So when coding on a GPU, think, I want to access a huge chunk of memory sequentially, if at all I can. and let the threads just go 1, 2, 3, 4 as the data memory addresses go 1, 2, 3, 4. So keep in mind, CPUs go down the call tree, GPUs take a single instruction and launch it across a bunch of different threads that all do the same operation. So that'll help you with memory accesses. So there are other programming models to use. In this case, I was showing CUDA Fortran, which has only been implemented by PGI, so keep that in mind. CUDA links up with most compilers pretty well. I think its backend is LLVM, and it plays nice with GCC. But this is similar to the examples I gave above. You're going to hand optimize this kind of stuff. This is a good option to use in the hotspots of your code. If you have a real tiny section of code that's doing a lot of work, go ahead and tune it by hand. If it's not going to require that much effort. OpenCL is a little more cumbersome than CUDA, but you write your own wrappers and it'll actually look pretty similar. They just have their own language. It works on all GPUs, not just NVIDIA, and it also works on multi-core. And whether or not it's performance portable, well, that's implementation based. That's always a work in progress for any language. The other option, use libraries whenever possible. These are people who have done the work for you, the painful work of taking reductions, summations, and things that would be otherwise awkward to code by hand, and you can just use their work and get it running. The thing to keep in mind is libraries, you can't be mindless with them. They're not automatic. You have to handle the data traffic between the main memory and the GPU DRAM across PCI Express. So it's up to you to make sure that it's already on the device, things like that. A lot of times, if you want the library to offload it for you, to copy, do the operations, and then copy it back, you're not going to get much of a win. You want the data to be on the device as long as possible to avoid that PCI Express cost. So directives, I think, are a pretty good option. With GPUs, the directives are mainly going to be called OpenACC. And it's a lot like OpenMP in nature. It's a more sustainable software development practice. Why? Because you don't have to maintain two sources. With CUDA, you actually have to maintain two different sources, so you better hope that they're not developing it too heavily. We also had that one, had to find that out the hard way. So this is an old slide. They're not as limited in usability. The API is not evolving quite as fast. It's pretty set, at least the main things that you're going to use every day. The API is fairly fixed at this point, and it's usable in most things except Fortran-derived types. You're going to run into some problems if your main data is in a Fortran-derived type. You can't transfer those with OpenACC very well. So keep that in mind. These are also not automatic. You will always have to change your code unless you build it from the ground up to expose tens of thousands of threads of parallelism per node, which most codes realistically have not. But you also might want to check in your field to see if someone's already ported the code, because they might have. So make sure you're well connected in your field. So luckily, most of the changes you change to get GPU performance are actually going to change the CPU as well. They're going to improve it. A lot of times when you increase threading and data locality on a GPU, your CPU is going to increase by usually 2 to 3x. So with our codes at Oak Ridge, when we show the speed up numbers, it's not always the fairest comparison because we merge the changes that we did for GPUs back into the CPU profile, and it speeds up. So your baseline is actually moving. There's also something to be aware of, GPU-aware NPI. This will do the PCI Express copies for you whenever you do NPI between two different GPUs on two different nodes. And not only will it do the PCI Express copies for you so that you don't have to go PCI Express to main memory, NPI to the other node, then PCI Express back to another GPU, and then go about your merry way. It'll do the PCI Express for you so you do NPI like you're used to and just put in GPU pointers. But if it's large enough, it'll actually automatically break it apart and pipeline it for you. So there's a lot of advantages if the vendor of the supercomputer you're using has GPU-aware NPI, where you can pass the GPU pointer directly in. You might want to use that. So let's move on to some challenges with GPU computing. So we've gone over this, but almost every application I know of is going to have to do some sort of NPI communication. Global arrays still have to use the PCI Express bus. You just won't have direct control over it, usually. All GPU to GPU transfers involve the PCI Express bus. It's unavoidable. They have roughly the same bandwidth, so the bandwidth isn't going to limit you that bad. Unfortunately, If you're just mindlessly pumping data through and you're not staging it and pipelining it, it's going to double the cost of transfer. So you want to break up your large transfers, you want to pipeline them, and you want to overlap these two as much as possible. Or just use GPU or Npi if they can do it for you. That's always nice. But the latency is 1,000 times larger than Npi, on Titan anyway. And I think that's probably true on most supercomputers. I'm pretty sure the Argonne latency is pretty nice on Npi. So be aware that your latency for PCI Express, you don't want to do a lot of small transfers. If your code is the type of code that does a bunch of small transfers, which unfortunately in the climate realm we do that, you're gonna have a hard time with the PCI Express bus unless you can overlap it with other computations, which we found a way to do, luckily. And a lot of applications have overlapped their PCI Express computation, either with MPI or with other transfers. You can rework your algorithm to better chunk the MPI communications. I've seen a lot of people do that. You can sometimes communicate a little more, store it up, and then you can hide the PCI Express cost. We've had applications that have done that and gotten some pretty nice numbers out of it. But this is your dominant constraint when you're moving to GPUs from a non-GPU viewpoint. This is the first place you look. Can the data stay resident on the GPU the whole time? That would be wonderful. Of course, with MPI, it can't, but apart from MPI, you don't want to be doing mass dumps of your data back to main memory. So the next thing you want to consider, this is the next challenge, is maximizing the DRAM bandwidth. You really want to access it contiguously. As your threads go from one index to the next, you want your memory locations to go from one address to the next. The PCI Express bandwidth, these are all GPU numbers. The bandwidth on the PCI Express bus is 18 times slower than the bandwidth on the DRAM. The DRAM is 48 times slower than the floating point throughput in double precision. It's, it's about 50% worse in a single precision. So it needs to be at least as fast as the GPU DRAM. If you're not maximizing the bandwidth on the GPU device, you're not going to get anywhere close to the performance you're wanting to get out of GPUs. So often, what we've seen done in codes is you'll take one array, you pull it out of DRAM and put it into shared cache to store to use later. Then you'll take you'll rework your indices with some simple integer arithmetic so that you access the next array in a contiguous way. Put that into shared memory, and then you do your computations in shared memory, where you can be as irregular as you want, and it doesn't actually give you that kind of penalty as you would get from main system memory. The worst you'll get is an 8x degradation improvement, which is actually that's actually not so bad. 8x compared to what, 48? It's better to do it in shared memory if it's going to be awkward accesses than to do it in DRAM. So a lot of times we've seen people just rework how they index mid-kernel and then do all your operations in cache. So the DRAM bandwidth is significantly lower than flops. Peak flops on a single precision Kepler GPU at the time was about 5 gigaflops. In double precision, it's almost 2. The peak memory bandwidth was only 36 billion doubles per second. So I'm going to go in double precision here, because that's what I'm used to working in. So how elusive is peak performance on a GPU? I would say entirely elusive. You're going to have 72 operations per data access. And remember, data access means a read or a write. So 72 operations per read or write, to me, in a straightforward manner, is almost impossible. You have to go high order, as you heard earlier, and you also have to reuse data in cache. So, even in double precision, it's 48 times, 48 operations per data access. So when you're programming, not just for GPUs, but for anything now, the one thing you need to be thinking about is, I spent all this time getting this piece of data, what am I going to do with it? You want to do as much as possible. When you're formulating an algorithm, you want to be thinking, what can I do with this piece of data now that I've fetched it from memory? So yeah, that small local cache is going to become your best friend when you're programming on a GPU, or really any architecture moving forward in the future. Everything is going to have the same type of constraint, no matter what it is. So even bandwidth limited applications, though, they're going to improve. Why? Because the GPU DRAM is 3 to 4 times faster than your main system DRAM. So even with stencil codes that are low order, maybe not the best programmed, if they're accessing the full bandwidth, from main system memory, they're going to see a speed up on the GPU. As long as you handle your PCI Express costs, you'll still see about a 3x improvement for that section of the code, which is a pretty good result. And we've seen a lot of codes that actually access that. A software engineering perspective, nowhere near the what you heard earlier, but do you have the staff available to refactor the code? That's something to consider when you're thinking about porting. What's the expected workload? How many hours are you charging that project to port this code over? And do you think you'll recover that cost with the lower core counts that you're submitting on some sort of allocation like Insight, ALCC, or Director's Discretion, or whatever your lab may have? Can you use directives? Because that would be a great way to go. Otherwise, are you willing to support two separate sources of code? With a code that's rapidly changing, you're really going to want to use directives. Mainly because you don't want to be constantly backporting the code through the main branch into your GPU branch. So how active is the development for the ported sections of your code? You want to get an initial profile. In the best case speed up, does it make sense for a porting effort? And a lot of times it does. A lot of the Insight codes that we've seen come into Oak Ridge, at least, have ported their codes to GPU with pretty good speed up. So, another thing to consider is, with the core hour allocations you can get, and also the kind of marketing you get from having ported your code to an accelerator device on future platforms as well, will it help you get the core hours you need to get the science done? This is not a straightforward optimization process. A lot of times, if you can use the hardware efficiently, you might get a leg up on another application that's not using the hardware efficiently, and you might actually get the allocation instead of them. So, there's a lot of things to consider when porting the code, but these are kind of software engineering and getting science out of it overall ways to think about it. I'm not going to belabor this one, except just to say there's a hierarchy of optimization. Number one, PCI Express, you want to overlap these, either with NPI or independent sections of code. You want to provide enough threads to occupy most of the GPU, at least enough to handle all the threads across the device. So my suggestion is tens of thousands at the beginning mark. You want to go up from there. So you want to make sure that the DRAM accesses are sequential. We've been there. Code uses in shared memory. Even if you do everything in shared memory, which we've had some cases of this, if you did everything in shared memory, it's already running so much faster than the CPU that even an 8x degradation in peak is not so bad. It's really not at all. But once you get down to doing everything in shared memory, if you can for your application, the shared memory is banked, and we can get into more of that later, or maybe we want to wait for the breakout session. But banked memory is something that is a little annoying to deal with. But if you do, you can get rid of this 8x, and the shared memory is actually as fast as the registers. If you handle the banking correctly. But that's kind of in the weeds of optimization. That may not be where you want to spend your time as a computational scientist, being a scientist first. So you heard flops are free. That statement really is true, but you need to understand what it means. It's there because the peak flops are so much greater than the peak bandwidth. It's 2 orders of magnitude and increasing. But I don't know many cases without a lot of thinking that you can add flops without adding data. Useful flops need data. So if flops require data and data is not free, then flops really aren't free, are they? So when you're thinking of actually changing your application, algorithms are really, in my opinion, where a lot of the magic is at. You can't add flops without data unless you change the algorithm, unless you change the way you're using the data. So you have different discretizations, you have different ways of formulating the way you evolve the equations. Some people will do it with a finite difference, finite volume operator. Some people do it with a Galerkin operator. You can actually do it with a multi-moment finite volume operator. There's a lot of ways you can do that. High order, there's a lot of things to think about here. There's a lot of creativity that really hasn't been fully explored, in my opinion. But if you can change the algorithm, and it allows more threading, it decreases data dependence within the threads, and it decreases local data requirements so that it fits in cache. If any of these three, especially all three of those, are true of you changing your algorithm, you might as well go ahead and increase the flops because it's actually going to win out in the end. Why? Because your data is transferred less often. So I encourage more flops as often as possible. We have a kind of case in point of this with a vertical remap operation where we have floating Lagrangian levels that are allowed to freely float as transport goes along. And then we map them back to a reference grid so they don't deform too badly. And so this remap previously used monotone splines and summation-based integrations. Splines are global in character. They require linear solve. They require nested loops that are dependent. And it really wasn't well suited for the GPUs at all, to be honest. So we just switched to something I was familiar with at the time, PPM, which is basically to say that we can keep it monotone, but it doesn't have to be dependent throughout the vertical column. We can actually thread that now, so it adds to the threading. It requires less data than splines, so we reduce data dependence. And we actually integrated twice over the interface. Instead of adding up summations and accumulating mass and then integrating once, we integrate twice. So we doubled the amount of work we had to do, and we actually got about a 6 times speed up compared to the optimized CPU code using PPM, which was already faster than the CPU code. So all in all, the effort of changing the algorithm and then porting it to a GPU in a smart way, keeping in mind the caching requirements, we got about a 12x speed up for this routine of the code. And so this is the way to be thinking about algorithms. You just want to constantly be thinking, what can I do with the data once I've gotten it? So regarding some of the opportunities there are for science that have already been realized, here's a small list of codes that we ported at Oak Ridge. There's LSMS, I believe it's a condensed matter physics code. This is the one that does a ton of computation across the whole machine and then outputs like megabytes of data. So it's a bit of a lucky application. But they use libraries. So they actually use cuBLAS, I think, or some kind of LAPACK on GPUs. They actually leveraged other people's efforts to get a pretty quick speed up of this code on GPUs. LAMPS is a molecular dynamics code. They used OpenCL instead of libraries. And they had a pretty significant speed up by changing the size of the data when they're transferring it across the PCI Express bus and within the GPU. But they got somewhere between 2 to 5x, I think, if you did an apples-to-apples comparison against the CPU. S3D was a code ported using OpenACC directives, those ones that are like OpenNP. This is a combustion code. Stencil operation, 8th order, finite difference, as straightforward as you can get in that manner, with some chemistry physics added to it. I don't know if they took the advice and put full chemistry instead of limited, but they got a good speed up using OpenACC. I think it was order 3x. And CAMSE is the code a team I was working on. This is a community atmosphere model spectral element, and we only ported the tracer transport, and our thinking was if we're going to use the GPUs, well, let's use the tracers as an extra dimension to thread over. And we got 100 times more threading out of that, and we got about 3 to 4x speed up for those routines. Across the entire application, it was more like 2x. And we use CUDA Fortran. De novo is a nuclear radiation transport code. And this one was using straightforward CUDA. They got a significant speed up. I can't remember what it was. And NRDF, I'm actually not that familiar with, so I won't comment on that. But on this slide with the team porting these things, we didn't actually plan this from the beginning, but we have 5 different methods of porting to GPUs. We have libraries, directives, CUDA Fortran, OpenCL, and CUDA, and all these. And they all gave good results. Results I would say would be worth the porting effort. So these are examples of codes we've had. There's a lot of Insight projects I've seen personally that have already ported their codes to GPUs. So there's a lot of expertise to kind of take from the communities, from experience that people already have porting the codes. So there's a lot to leverage so far with doing this. But GPUs is giving a lower power, high performance option for getting science. And with that, I will take any questions.